Welcome back. Here we go again. Let's do that last weak acid practice problem. All right. What will the pH of a zero point 0.1 molar nitrous acid solution be if the Ka is 6.0 times 10 to the minus fourth? Basically, it's the same question as before. It's just phrased a little bit differently. All right, nitrous acid in this case. And that's pretty short to write, so I'll put the whole formula. Ka is equal to proton nitrite all over HNO2. And then I know the Ka is 6.0 times 10 to the minus fourth. Okay, did I get any information to put in my ice table? It looks like the original concentration is 0.100. Didn't add anything to it. Changes by a negative x and a positive x. So 0.1 molar minus x, and x. All right, I have enough information in order to plug it in to the equilibrium expression. So 6.0 times 10 to the minus fourth is equal to x squared over 0.100 minus x. I'm going to do my assumption, x. I'm going to multiply 6 times 10 to the minus fourth by 0.1 and square root it. And 7.7 times 10 to the minus third. Plug that in again. 7.7 negative third. All right, I'm going to double check. Make sure my assumption was valid. Uh-oh. In this case, that is not a valid assumption because it is larger than 5%. So do we panic? Nope. We can either go back and we can do the quadratic, or we can do something called successive approximations. So let me change colors here. So if the answer is no, you may either just go plug it into the quadratic, or you can do something called successive approximations. And whichever one you do is absolutely fine. All right, got to remember my numbers here. It's 6, negative fourth, and 0.1. I'm going to go over to the whiteboard. Where are you, whiteboard? I don't think you guys can see that. How about I just hit the button, 6 billion times? Okay, there we are. So right now we have HNO2 plus NO2 minus, and 6 point, see, good grief. I'll go back and check that. 6.0 times 10 to the minus fourth is equal to proton nitrite over HNO2, and it was 0.100. And so 6.0 times 10 to the minus fourth is equal to x squared over 0.100. Ignored it and came up with 7.7 times 10 to the minus third. And we came up with the answer no. All right, so all I've done right now is rewrite everything I had before. All right, so this is the way we're going to do successive approximations. We are going to plug the answer that we just got in for x back over here. Okay, so I'm going to go 0.1 minus 0.0077. And I come up with 0.923. And I get to keep 3 after. 1, 2, 3. So 0.092. Now, the reason that I did that is I'm now going to plug it in and see if that was a closer number. So again, I go back to the 6 times 10 to the minus 4th. That k value didn't change. And the x squared is fine. But instead of using the 0.1, I'm going to use the 0.092. I am going to ignore. And this x turns out to be, and I put -5 right there. It's supposed to be a -4. So 6 to the -4th and 0.092, square root it, and I come up with 7.4 times 10 to the minus 3. All right, it's still not okay, but I'm doing successive approximation, so I'm okay with that. I then go plug it in one more time. My original concentration minus this new x. Zero 0.0925, and so this one's going to round up to 0.093, and I'm gonna plug it in one more time. Six to the -4th, 0.093, and I get 7.5. All right, if you will notice, that number is starting to go back up. That's what successive approximations means. You keep narrowing it, narrowing it, narrowing it until that answer doesn't change by very much. So the true answer lies somewhere between those two, but we only get limited sig figs. So as far as we're concerned, you can use either of those numbers. So for successive approximations, you keep going. You go until you become less than 5%, which probably isn't going to happen, okay? Or the number goes up or stays the same. So in this case, we had a 7.7, and then it went to a 7.4, and then it went to a 7.5. So this one went up just a little bit. And so this would be the best number to plug in. Now, I'm not going to do the quadratic, but if you do the quadratic, guess what? That is the answer that you get from the quadratic equation. Wow, after all that, what in the world was I even looking for? I'm looking for the pH. So I'm going to go plug those numbers in. So this one is going to be 0.092 molar, and this one is 7.4 times 10 to the minus 3. And 7.4 times 10 to the minus 3. And my pH is the negative log of 7.4 times 10 to the minus 3. and I get a 2.13. Plug it in again. 2.13, and I was expecting an acidic pH, so that looks correct. All right, so the reason that we had to do all this extra work is it did not fit our assumption. It was greater than 5%, so I could have used the quadratic, but I used something called successive approximations. So I took the X I found and I subtracted it from my original concentration, and then I did the problem again, and I do that until I get a number that is valid and less than 5%, or the number slightly goes up or it stays the same twice. And if it does go up, I tend to take the number before it goes up. And in this case, if you do the quadratic, that is the exact answer. And last but not least, I should have done this before I went on, it is greater than 10 to the -6, so it was okay to ignore that ionization of water. All right, there is the fourth and final problem as an example for weak acids. Until next time, jolly out.